So awesome, topic 1 is done. We've covered a lot of content there, so hopefully that was a helpful overview for you. If you do need to take a breather at any point, please feel free to pause the video. But for now, we will be moving on to topic 2, which is time series analysis. And the awesome news that I have for you guys is that time series analysis, topic 2, is actually a lot smaller than topic 1. There's still some challenging concepts in there that can take you a little while to wrap your head around. But for a lot of it, it is actually quite similar to our topic 1, our bivariate data. And you can probably start to see a lot of that similarity right here as well, because our time series plots, which is what we call these, where we plot our time series data, are actually quite similar to our scatter plots, with one of the main distinctions being that when we're doing time series analysis, our explanatory variable is always a measure of time. So whether that be seconds, months, weeks, minutes, even decades, just some sort of measure of time. And then because our explanatory variable, which we always plot down the bottom, is some sort of measure of time, then whatever our response variable is, what we're looking at how something changes in response to passing time, that's why our other variable in this case is always going to be the response variable, because the thing that is driving the change in time series analysis is always time. So that's why time is our explanatory variable. And then whatever our other variable is the response variable. And then also we actually connect the dots, whereas we don't do that in a scatter plot, and it would make our scatter plot quite messy. But because with time series analysis, we only usually have like that one data point, that one recording for each time point. And because time is like a continual, precise, linear, and unchanging relationship, that's actually why we can connect the dots. So it's quite similar to a scatter plot. We've got our explanatory variable down the bottom, always going to be time, our response variable on our y-axis, and then we just plot our points like normal. We connect them. We can even add a least squares regression line. So there's a lot of similarities there, which is quite helpful. And there's another example of a time series plot just there. So again, a time series plot is a representation of time series data, which is just when a variable is recorded at successive time intervals. So we're always interested in how our response variable is changing over time. So for example, think about temperature. We could map how temperature changes throughout the year, or we could map how ice cream sales change throughout a week, or throughout a day, or throughout a year. And then think about the patterns that we might see because of that. So again, making that really active link. We're always looking for those patterns and relationships. We're always looking for how can I draw meaning from this data. We're not just interested in putting it on a scatter plot or a time series plot to make it look really pretty. We're actually looking for how can we draw meaningful conclusions? How can we interpret patterns and relationships to learn more about whatever it is that we're looking at? So again, we're looking for certain features. So to kind of make that connection again, in scatter plots, we were looking for, do you remember the 3 categories? It was the direction, strength, and form. When we're discussing time series plots, we're looking for different features. And the syllabus, which again I've linked here, tells us what features we're looking for. So here we can see that under our first kind of sub point of the time series analysis, you need to be able to construct time series plots. So by breaking down kind of the key features of a time series plots, hopefully you're already feeling a little bit more equipped to do that, and practice helps with that a lot as well. And then the second point is that you actually need to be able to describe time series plots by identifying features such as trend, which the syllabus defines as like long-term direction, so that overarching like pattern. Seasonality, which is systematic calendar-related movements, talks about irregular fluctuations and also outliers. So you can kind of see all of the different terminology that if in an exam question you were asked to discuss a time series plots, this is the different language that they're really expecting you to be able to bring in. And this, again, if you want to take a screenshot or download the slides, is just a really helpful kind of condensed kind of summary of what each of these are. So again, trends are our overarching patterns. It's the tendency for our values to generally increase or decrease over a significant period of time. If you are asked to kind of analyze or make a statement about a time series plot, trends are always a really good one to discuss because most time series plots do have some sort of trend. And depending on what our response variable is, will depend on what our conclusion is about what's happening over time. Our second one is seasonality. So when we're talking about seasonality, we're thinking calendar patterns. So it might just, the first thing that springs to mind with seasonality might be summer, autumn, winter, spring. And that's totally okay if it is, because that's still what pops into my mind straight away. But the important thing to keep in mind is that seasonality, it's actually not just about those 4 breakdowns of the year. A season can actually be any calendar related period or breakdown of time. So a season could be a week, for example, because there are 52 weeks in a year. A season could be a day because there's 365 days in a year. Or a season could be a 3-month stretch, like how we typically understand seasons to represent. So again, seasons are our calendar patterns. So they're our predictable calendar patterns. They're usually pretty predictable, and we're normally talking a year or less. Whereas cycles, our next kind of terminology, is more those longer term patterns, so usually greater than a year. So for example, if we were looking at certain trends or patterns over decades, we're more looking at cycles than seasonality. So that's just that distinction there. And if we have a structural change, this is actually an example of a structural change here because we had an established trend or pattern in our time series plot, and then we had a structural change around time point 13, and that actually resulted in a new trend or pattern being formed. And so that's kind of what we're talking about when we're talking about a structural change, and that could often be reflected or explained by external events. Next one, outliers, probably pretty familiar with. It's just a single unexplainable point that stands out from the rest of your data. And just to kind of make that point clearer, if you follow my laser pointer, so our structural change example we looked at was when we had a continued pattern, and then we had a structural change, and then we had a new pattern. But if, for example, we had an outlier, it would kind of be we're following with our pattern, we've got one outlier, but then we go back to our regular pattern. That's kind of our difference between our structural change and our outliers. And then lastly is irregular fluctuations, which is essentially everything else, all things unpredictable, unexplainable, and present in any real-world data. So I know that's a lot to think about, and you might be able to come up with some helpful mnemonic or something to help you remember each of the things you might be able to discuss in a time series plot. And sometimes it can just take a bit of practice to kind of get a bit better at identifying these things when you do see them in a time series plot. So yeah, that's a lot of different things we can talk about. So when we're looking at a time series plot, you've already got all of these different things going on in your mind, but we're going to bring in another factor now. So bringing it all together a little bit. Hear me out. So what if we wanted to remove the impact of irregular fluctuations, or if we wanted to remove the impact of seasonality to try and see, is there actually an underlying pattern that's being obscured by these things? And we can. So that's actually how we link in smoothing and deseasonalizing data. So again, I'm trying to help you make these connections. So when we're talking about irregular fluctuations, we're talking about kind of those random ups and downs that might kind of obscure the underlying relationship. And so it can actually make what's actually going on really hard to see because it's kind of obscuring it. It looks really messy up and down. But if we apply smoothing, we can actually remove the effects of that and kind of look for those underlying patterns and trends. And then same, if we have seasonality present in our data, by deseasonalizing it, we can actually remove the impact of seasonality so that we can see if we put the impact of seasonality aside, do we actually have any trends or patterns there. So smoothing, we have the 3-moving average or the 5-moving average, also kind of referred to as the 3-moving mean or the 5-moving mean. Probably familiar with those terms. And we can also do the 2-moving mean and the 4-moving mean, but when we do it that way, we need it with centering, which we won't be going into it either today for the sake of time. So again, the idea behind our 3 and our 5-moving mean The name comes from how many points we're taking the average from. So with a 3 moving average or the 3 moving mean, it's 3 because we're taking the average of 3 separate points to get the average value for our starting point, and then we do that all the way through our data. So that we kind of get that effect of like, because we're taking all these averages, we're kind of in effect like we're smoothing out the data. Think about it like we're ironing out the irregular fluctuations. We're removing them. We're trying to get rid of them. So we actually can't take the 3 mean smoothed value for January, because if we were going to do it for January, we'd need to take the point for January, the point before, and the point after. But we don't have a point before January, so we actually can't do January. So January is off the table. But we can do February by taking the value for February, the value for January, and the value for March, adding them together, 12, 8, 7, which gives us 27, which we divide it by 3, because that's a number of, like the number of values that we've taken, and that gives us 9. So our 3 mean smoothed value for February is 9. And then we can find the value for March by getting the average of February, the average of March and April, adding them together, 8, 7, and 14, add them together, divide them by 3, just like with any other average, and we get 9.67. We can do the exact same all the way through. And we can also do the exact same with the 5 moving average. The main difference being that we actually lose our first 2 data points when we do a 5 moving average. And that's because again, we don't have 2 points before January to use. We don't have 2 points before February to use. But when we're looking at March, we can take March, we can take the 2 points before and the 2 points after, divide them by 5, add it all together, and then we can actually get the smoothed value for March. And once we've done all of our smoothing, it can be a bit of a time-consuming process, and that's why it's usually kind of handy, kind of convenient and nice and neat to kind of do it in a table or whatever kind of format works best for you. But once we have all of our values, we can actually plot our smoothed value on our time series plot as well. And that's actually super helpful because it actually makes it really, really clear like if there is like a trend or a pattern or a relationship that it has uncovered. And we've got a key here. So we can see that this here is our original data, and you can definitely start to see what I'm meaning by like irregular fluctuations. We've got all these crazy ups and downs. I actually can't really see if there's like a pattern or a trend there because it's just so up and down and obscured by these annoying like irregular fluctuations. So what we've done is we have applied smoothing, and you can see here we've got our 3 point and our 5 point. But because it's actually in black and white, it's kind of hard to tell like which is which. They look quite similar. We've got like our circle and our square. But another way that you can kind of tell the difference between them is by looking at how many points there is. Remember what I said before about how when we do the 3 moving mean, we actually lose the first point, which here is January, and the last point, which is December. So I can actually really easily tell, even without looking at my mean, that this must be my 3 moving mean smoothed data because I've lost my first and my last point, which means that this line here must be my 5 moving mean because I've lost my first 2 points and my last 2 points. So that's kind of the difference there. So we can start to, and as we look across at the different kind of lines, we can actually really clearly see the impact that our smoothing is having. You can actually kind of see that ironing out effect, that smoothing down. We're kind of ironing out the irregular fluctuations because we can see our 3 point mean smoothed line here. We can actually see that a lot of these crazy high irregular fluctuations have kind of really been, like we've said, been ironed out by taking those averages. And our 5 point line has been even further smoothed. Those really big variations have been even further ironed out. And if we have a really close look, we can actually start to see that maybe there almost is a bit of an underlying trend there. Because if we were to fit a trend line to our 5 point smoothed data, we actually might even start to see that maybe there is a little bit of an increasing trend there. Because now that we've got the effects of our irregular fluctuations moved out of the way, we can kind of start to see that a little bit more. So that's really interesting there. Again, we won't be touching on that. So that was removing the impact of irregular fluctuations. But if we want to remove the impact of seasonality, this is where deseasonalizing data comes in. And how we do that is with seasonal indices. So we won't focus on here too much because I would like to focus more on sequences. But the main things I'll draw your attention to is, again, that a season is any breakdown of time with equal periods in the year. So again, if we could do it month by month, in which case we'd have 12 seasons in the year. And seasonal indices, which are like the numbers that we use to deseasonalize and reseasonalize data. So these seasonal indices, what they're doing is they scale information to reveal trends without the influence of seasons. So if, for example, I had a time series plot where I plotted ice cream sales throughout the year, you'd definitely expect there to be a big spike in the summer months, and then in the cooler months, I probably wouldn't be selling so many ice creams. So if I wanted to know, is my business doing well because it's summer, or is my business doing well if we removed the impact of temperature from our data? That is where like deseasonalizing would come in. So that is, again, it's just removing the impact of seasonality. So that, yeah, like I said, we can see, is our business doing well because it's summer, or is our business doing well in spite of the fact that it's summer? So again, removing that impact of seasonality. And again, it makes our data more readable. So a seasonal index is usually a number around 1, because seasonal indexes are based around that average point being 1, and the sum of your seasonal indices will always equal the number of seasons. So if we're looking at days in a week, we'll have a seasonal index for Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. And the sum of all those numbers will add up to 7. And any of the points, any of the seasonal indexes that are below 0 means that it's a below average day, and anything below 1 is below average, and above 1 is above average. So for example, a seasonal index of 1.3 means that that season is 30% above average. So if I said, for example, if we were doing like ice cream sales throughout the year, and if the seasonal index for summer was 1.3, that'd mean the seasonal index for that means ice cream sales in summer is 30% above average. So that's really important to keep in mind, that when we're interpreting seasonal indices, we're always coming back to what actually is the average. That's what we're coming back to. This is our formula to calculate the seasonal indices. So the seasonal index, so that number, that'll probably be around 1, a bit below, a bit above 1. Our seasonal index is equal to the value of the season. So for example, the number of ice creams sold in summer divided by the seasonal average. So that's, again, the seasonal average. You've got to calculate that before you can find your seasonal index. Again, a quick reminder that if you add your seasonal indices together, it will equal the number of seasons. So that can be helpful if you've got to find an unknown seasonal average as well. And again, if it's 0.87, that means that it's 13% below average. We're always coming back to the average. Like with any formula, it can be rearranged. So if we have our deseasonalized value, but we want to reseasonalize the data to get back to the actual value, again, we can rearrange our formulas to do so. So I know I haven't spent too much time on that. We haven't gone in depth of how do we calculate seasonal indices. But again, that's definitely, I'd encourage you to do some practice questions on that and find some helpful videos and resources if you are wanting to do some extra study on that. And again, another little connection. If we did want to add a least squares regression line, like a trend line, to a time series plot, we definitely could do that to help kind of highlight those overall patterns and trends. So again, just making more of those connections.